Okay, we can go ahead and get started. Happy to introduce today's Colloquium speaker. Dr. Berger's got his PhD in physics in 2015 from the University of Michigan, and he worked there, I think it was with Duncan Steele. And he worked on quantum optics with quantum dots. He's currently a postdoctoral fellow or scholar at California Institute of Technology in Jeff Kimball's group. And he's going to tell us today about engineering atom-light interactions with photonic crystal waveguides. So thank you.
Thanks. Okay, well, I want to thank everyone for having me today. I've had a lot of really interesting conversations with all the people I've met with, and so it's been a really good visit. So, what I want to talk to you today about is kind of the work that I've been doing in Jeff Kimball's lab at Caltech. And so, as Jason mentioned, engineering atom-light interactions in photonic crystal waveguides. But to begin, I want to start with kind of some motivation as to why not only would you study these kinds of systems, but why you would study atomic systems in general, and some of the things that you could do with these systems. So, just to start out, what we'd really like to do in this field in general, in the field of quantum information science, is to utilize the quantum nature of light and matter, that's atoms and photons, to investigate new quantum technologies. So, for example, quantum computation and quantum communication. And also, we may be able to actually simulate quantum systems. So, sort of famously, Feynman kind of introduced this idea that these quantum systems could actually would be the only ways to really simulate complex quantum systems. And so the way that we can do this is by utilizing the quantum nature of this state. So if you have some quantum state psi, it can exist in a superposition of up and down or 1 and 0. It doesn't have to be an atom with a spin. It can also be the polarization state of a photon. And by utilizing this nature, you get speed up in kind of quantum information processing, looking at things like factorizing numbers. So Shor's algorithm is kind of a famous example of this. And one thing that you can also utilize is that quantum states exhibit this entanglement feature. So for example, a photon emitted from an atom is going to carry with it information about the internal state of that atom. And so by trying to take this quantum state psi and distributing it amongst a different or a large system of nodes, we can distribute this entanglement from one system to a bunch of systems, and that actually allows us to kind of realize quantum technologies on a larger scale that's not just atoms, single atoms, and single photons. So, we'd send in a photon here, and then these states would become entangled, and then you can do it with larger systems here. And so now you've kind of built this network where all of these nodes become entangled with each other, and that really speeds up the ability or improves your ability to do these kinds of quantum information protocols that I just talked about. So most of the advances in this kind of field really come from getting strong atom-light interactions. So strongly interacting some kind of, like for example, a laser light with an atomic system, and then connecting these nodes that I described earlier with different, using some inherently quantum channels. So here's just an example of an atom. It's inside a cavity, and it's connected to another atom in another cavity somewhere further away by maybe some optical fiber or some kind of photonic channel to mediate this interaction. And so a lot of the work that's been done in this field, the work that actually Jeff Kimball, my postdoc advisor, did quite a while ago, was to really try to achieve this strong atom-light interaction. So get the light that you would send into this cavity to strongly interact with the atom inside of it. So I'm kind of going to talk about what atom-light interactions, and so we're going to utilize a single atom as the nonlinear element for this quantum information processing. So that would be one of our nodes, for example. And this atom is a ground and excited state, and they're coupled by a dipole transition, and it just has some wavelength lambda Eg, for example. And you can try to talk to this atom in free space by using kind of a resonant laser to address the atom, and you can write down the probability of interacting with this atom, and that probability just goes basically as the cross section of the atomic transition over the area that you're able to focus down to. And it turns out this, you can actually get decent interaction with the atom here, but the strength is not sufficient to do the kinds of operations that we'd like to do in any kind of quantum memory or quantum information context. So what people, a couple of the problems really are that the free space mode overlap is not ideal, and a lot of this information ends up being radiated away outside. And so you'd have to create kind of a 4-pi detector to get all of the information that's scattered off of the atom. And so what people have done is, just increase the number of chances you have to interact with this atom, and that's just putting a cavity around it, and then you increase this this figure of merit by basically the number of trips that this photon takes back and forth in this cavity, and then you can you scale up your interaction probability in this way. And this is known as the field of cavity QED, and so I'll write down some of these parameters, but really the thing that's important to take away from this is that there's this figure of merit called the cooperativity, and all it's really telling you is the ratio of the good coupling in the system to the bad coupling in the system. So the coupling so for example, this 2G here is just the single photon Rabi frequency, which is really just the coupling of the atom to the cavity. And then this kappa gives you kind of the line width of the cavity, the information about the decay of the cavity, and then gamma prime is just the emission of the atom into free space. So it's the information that's essentially lost. And so if you can increase this coupling G squared, then you can kind of beat down this gamma prime, which is just the loss of information into free space. And so whenever you see something kind of like this cooperativity, really it's just a measure of how good you're doing, the ratio of good to bad, essentially. And so I just want to give an overview kind of conventional atom-light interaction. So I talked about this kind of tight focusing where you can get an interaction that's kind of not exactly very good for the kind of quantum memories that we want to create, and of course cavity QED that I talked about before. You can do some other things where instead of doing one atom strongly coupled to a cavity, you just have a whole bunch of atoms, and now the figure of merit kind of goes as the optical depth of the system, or how well your laser is attenuated through the system. And by utilizing different energy structures, you can create also quantum memories for these. So these would be situated at each specific node of the kind of quantum internet web that I talked about earlier. You can also use Rydberg ensembles, so highly excited Rydberg states, and these will cause very strong nonlinear responses in these Rydberg clouds. And so these are kind of the traditional sort of conventional atom-light interactions. So a question that you could ask is, are there other systems that you can investigate that would strongly couple light to atoms? And one such system is to try and couple this atom to a nanofiber. So this is just a piece of this is meant to represent just a piece of fiber that's been pulled down to a very small diameter, and this atom will interact with this structure, and actually it'll decay into a guided mode of this waveguide. And now, instead of talking about in the context of cavity QED with this cooperativity factor, you can write down kind of the one-dimensional decay, or the decay of this atom into this fiber, and you can write this down as this gamma 1D factor. And it's given by the following parameters. So the Einstein A coefficient of the atom, so the decay of the atom, the mode overlap. So you send a guided mode into this nanofiber, and it'll have some evanescent properties, and the atom will actually sit in these in the evanescent modes of this fiber. And so that would be the mode area, and then the group velocity of the light inside the fiber. And of course, the cross section's just the same as I mentioned before. And so what you can think about in these this is known as waveguide QED, for example. And what you can think about is, or you can think of gamma 1D as kind of analogous to G squared over kappa, which is kind of like the coupling of the atom to the structure itself. And then this gamma prime is just the same as it was before, which is the information or the scattering that's lost out into free space. And so for this kind of a system, the kinds of ratios of good coupling to bad coupling that you can get for a single atom is kind of roughly 0.04 or so. Said in a slightly different way, if you send light into the resonant light that's on resonance with the atomic transition into the fiber, and you have a single atom coupled to this fiber, the light will be attenuated by 10%. So this is transmission with the atom versus transmission without the atom. This is actually kind of not necessarily a great factor here, but one of the things that you can do in a system like this is just increase the number of atoms. And so now your figure of merit kind of goes as the number of atoms times this gamma 1d over gamma prime factor. And so there are some interesting things that you can do with atoms coupled to these waveguides. For example, at specific spacings of these atoms, you can create a Bragg mirror. So light that goes into the nanofiber will be completely reflected off for the atoms that are in this kind of mirror configuration. So that's for specific spacings of the atoms. And one reason why that's interesting is now you've kind of created this mirror that's actually built up of these quantum pieces. So the atoms are actually acting as an optical element. And so you can construct a system where you have, for example, atoms in a mirror configuration on one side and a defect atom in the center, and then atoms in a mirror configuration on the other side. And now you've replaced the free space Fabry-Perot mirrors from cavity QED and put in place atomic ensembles as the actual mirrors that will be in your cavity QED system. And I mean, this is a pretty interesting physical phenomenon to try and do. But one of the reasons why you might want to actually implement it is that on the same nanofiber, you could imagine constructing a system that has sort of one kind of cavity QED system on one side where you have atoms in the mirror configuration, a defect atom, and then again atoms in a mirror configuration on the other side, and then build up on one fiber a bunch of these kind of cavity QED systems, for example. And then it really starts to look like this kind of system that I described at the beginning, where you have one node here and then connected by some photonic channel, and then another node on the other side. And so a further question that you could ask is, well, the coupling wasn't all that great for these atoms to these 1D waveguides, so is there a system that we could construct that takes advantage of strong coupling of single atoms to a structure, whether it's this cavity, and the fact that we can put a whole bunch of atoms on a waveguide and utilize these kind of on waveguide types of quantum memories that I just talked about. And then also, one thing is, could you actually utilize this sort of system to realize new ideas in atom-photon physics? And so I think the answer is yes, and I'll try to convince you of that for the remainder of the talk. So what we've looked into doing in our lab is to actually couple these atoms to a 1D photonic crystal. So it's just a piece of dielectric structure with an index modulation, whether it's holes or so holes inside the dielectric structure, or in the case of what I'll show you next, we actually modulate the dielectric structure. But this structure has a dispersion relation, so it has it has a band gap. There are states within the structure that photons cannot propagate or light cannot propagate in these specific frequencies. And so what we want to do is couple our atom to this structure. So for these structures, we use the language of waveguide QED as before. So we're still talking about this kind of gamma 1D that I described previously. But now, as the atom the atomic frequency is placed really close to where these bands curve, you end up getting an enhancement in this gamma 1D because the light in this region becomes very slow, and so this group velocity becomes very small. And so now, with atoms strongly coupled to these photonic crystal structures, we're able to to get gamma 1d over gamma prime of roughly 10, which is kind of orders of magnitude larger than what you would have in a standard nanofiber. And said in the same, in kind of this different figure of merit, transmission with an atom in this coupling regime versus transmission without an atom in this regime, you get kind of 0.2% for the transmitted light of a laser that's on resonance with the atomic transition. So we don't just want to couple one atom to the structure. We want to couple multiple atoms to the structure and look at interactions between these atoms in the dispersive regime. So an atom in some excited state, like the ith atom in the excited state, can emit a photon. That photon can then interact with sort of the next atom. And now these atoms are kind of exchanging interactions with each other, mediated by the waveguide. And this atom is freely propagating, and it gives you this. You could write down a Hamiltonian that talks about that tells you about the evolution of this system, where these sigmas are just the operators that take these atoms from ground to excited state. And also there's and then this one can go back into the other one. And you can build this up with a whole bunch of atoms, and they're all really talking to each other via the guided modes of the structure. There's also collective dissipation in the system, and that's dissipation of these atoms into the guided mode of the structure, and that gives rise to things like superradiance for multiple atoms coupled to this system. And so you can utilize that to create things like quantum memories, for example, and I'll talk about that in a second. But one further thing that you can do with this system that maybe you would have thought, okay, is eventually going to happen, is we can take this atomic transition and put it inside the bandgap. And it's actually not we're actually taking the bandgap and shifting it so that the resonance frequency lies inside. And this is not a new idea. I mean, in the 90s, people, when photonic crystals were first coming into the thought of physics experiments, people thought about what would happen if you took an atomic transition, and placed it inside the bandgap of a photonic crystal, and it just took really a long time to kind of, for all of the technologies around cold atoms and around nanophotonics to build to the point where it was feasible to really think about what we would do in this situation. But what ends up happening is that the photon is actually exponentially localized around the atom, and so it has no propagating modes of the structure to decay into, and that causes it to have this localization packet. Now, it still has the ability to decay into free space, so that's something that we need to always think about. But now, if you have, for example, two atoms and their photonic wave packets are overlapped, they'll start to exchange interactions with each other the same way that we saw before. But now the collective dissipation is suppressed. So the only thing that's really occurring in this system, absent losses out into free space, is just these atom-atom interactions. And so this begins to look a lot like the kind of thing that has applications in quantum simulation, for example. So, being able to simulate, I mean, in 1D it's maybe not very interesting. You kind of look at sort of an Ising model idea. But if you extend this out into 2 dimensions, then you can start to really build up more complicated Hamiltonians and more complicated structures. And then you can just extend this out into multiple, and then your Hamiltonian just grows in this way. So, like I said, this can be extended out into 2 dimensions, and this gives you kind of a different regime than you would normally see in conventional optical lattices, because now these atoms are going to be coupled to not only this nanophotonic structure, but the actual structure itself can have a scale of this lattice that's much less than lambda by 2. So the atoms will sit in trap potentials that are much closer together than you would get in a conventional optical lattice. And you can study Bose-Hubbard physics. I was having a discussion today. It's maybe not, I mean, this has been studied pretty extensively with really heroic experiments in quantum gas microscopes. but it would be a way to utilize this system as a kind of a check to make sure and to see that we're able to reproduce at least the kinds of experiments that people are able to do in these traditional free space optical lattice systems. And what's different about this is that the interaction energy and the tunneling rates for these are much, much larger, or could in principle be much larger than you would be able to get in traditional optical lattice experiments. And so what's important is that these factors are really just driven by the structure itself. So how good is your fabrication, your detuning from the band gap, the distance between these holes, all of it is something that you can do in lithography as opposed to, as I said, these free space things. So probably the more interesting thing to look at would be try to realize spin-spin Hamiltonians for quantum magnetism. The thing that's interesting about this type of idea is that inside the band gap, this coupling constant or coupling here, J, goes as this kind of complicated structure, and it's really not important to understand exactly all of the fine details of this. But essentially the idea is that all of these factors come from the structure themselves. So these structures you're able to engineer the structure to kind of do what you would want in these systems. So another thing is it doesn't just have to be square lattices. You could make hexagonal lattices, triangular lattices. It's really limited by the lithography that you're able to do in the nanofab. Okay, so I want to change gears for just a bit and talk about these like collective effects in atoms and how we could maybe exploit some collective effects in these photonic crystal systems. So one of the things I mentioned is this decay into free space is a problem. And while that's true, there are some things that you can do to try and turn that off. So in these ordered arrays where the distance between the atoms is less than lambda by 2, it turns out that the emission into free space is suppressed due to interference. So all of these atoms lining up, if they're less than lambda by 2, their emission into free space will be essentially cut off. And if you send an excitation into this system, then it really just becomes a guided mode of the chain. And this is, an interesting thing to study maybe in free space, but if you couple this to a photonic crystal structure, then this guided mode of the chain is now becoming a guided mode of this photonic crystal structure. And so now this excitation is going back and forth in this structure. And this has really important implications for quantum memories. So for quantum memories, the losses into free space are kind of your error rate, essentially. And if you can turn those losses off and increase the coupling of the atoms to your structure, then you can achieve this kind of known as selective radiance, just selectively choosing the radiant modes that are coupled to the structure. You can gain a much more favorable scaling of the errors in a quantum memory. So for a standard quantum memory, the infidelity or the error rate kind of scales as 1 over the optical depth, which is basically just 1 over the number of atoms times some, this gamma 1d over gamma prime times this coupling. But by utilizing the fact that you can turn off a lot of the emission out into free space by utilizing this subradiant effect, you can get an exponential scaling in the infidelity. And so what's important is that, this scale length is, of course, very important. But in the system that I'm going to show you, the atoms will actually, the trap sites of the atoms do lie at less than lambda by 2. So this is the kind of thing that we could exploit in these photonic crystal waveguides. Okay, so now I'm going to talk about our approach using photonic crystal waveguides. So it's not just this cartoon picture. It's much more complicated than that. We tried holes. It didn't really work out very well. So we used 2 nanobeams where the external, we place an external modulation. So that's the index contrast that gives rise to this photonic band gap. we want to trap atoms in the vacuum gap between these two nanobeams. And this is where we will, trap and manipulate the atoms. And so we call it this for obvious reasons. So there are have been two approaches that have really tried to couple atoms to nanophotonic structures in the past. So one is this is an experiment done in Misha Lukin's group at Harvard, where they take a tweezer and place a single atom really close to a photonic crystal cavity, and they're able to do this pretty deterministically and achieve kind of a strong coupling regime to this structure. And our group in the past would do something somewhat similar, but instead we would kind of utilize this side illumination beam, which is basically just a laser beam that reflects off of the top of this Alligator waveguide, and we trap atoms in the first intensity maxima just above the waveguide. And so with this technique, we're able to kind of trap roughly 3 atoms, and of course with the tweezer technique, you're able to really only trap 1 atom, and that's by design. But this isn't really what we want to do to push this forward. We want to achieve this high fractional filling of atoms inside the waveguide, and we really want to fill these sites up with atoms kind of at every single trap site. So how are we going to do that? Well, the atom that we're going to use is a cesium atom, and so I'll just give you the level structure. It has 2 basically strong transitions, called the D1 transition and the D2 transition, 894 and 852 nanometers. And the waveguide is actually, or the photonic crystal waveguide is constructed in such a way that its band gap lies, or the band edges lie between at the cesium D2 and the cesium D1 transition. And the reason why that's important is because it means that there's going to be regions of very high intensity and very high contrast for one of the transitions, and then at the other band edge there'll be regions of high intensity and high contrast for the other transition. And so we'll utilize these 2 colors to trap and manipulate the atoms. And so I'll mention also this is there are actually two propagating modes in this waveguide. There's the TE mode, which kind of propagates along the waveguide, and then the TM mode, which kind of pokes out the top of the waveguide. And I mean, the TM has a band gap, but essentially for all of our purposes, you can think about it as just a waveguide mode. So kind of basic. So we're going to utilize the dipole force to trap these atoms. So just basically, when you have a dipole transition and you tune a laser blue of the transition, the atoms will be pushed away from the regions of high intensity. If you have a red, or if you take a laser and park it at red of this dipole transition, the atoms will be attracted to these regions of high intensity. And also their levels will shift as well. And so we're going to utilize that to actually create this 2-color trap. So at one of the, so for example at D1 in the cesium D1 line, we'll place our laser blue of this transition, so the atoms will be pushed away from these regions of high intensity here into this region, where they will be attracted by this red detuned laser that's on the D2 line. So they'll be kind of pushed away from one region and sucked into the other region. And you can calculate using COMSOL, for example, what these traps might look like in different directions. So we have these sort of stable trapping sites at all of these regions within this photonic crystal waveguide. Okay, so now so talk about the experimental implementation of this. So this is the device and the support structure. We use an optical fiber to couple into and out of this system. The optical fiber is kind of glued into these V grooves, and you can maybe actually make out the nanobeam that goes along this direction here, and then it's being suspended across this V groove here. And so This allows us to bring light into and out of the sample. These node tethers actually act to support the structure and dissipate heat. So we're utilizing these different colored traps, and that's going to that's going to cause a lot of heating in the sample. So these kind of help to dissipate the heat and support the structure itself. So to move from this 1D waveguide into this photonic crystal region, we utilize this kind of mode matching or tapering of this dielectric modulation and that allows us to kind of effectively mode match from, or impedance match from, this kind of 1D waveguide into these two beams, because it's actually a pretty drastic change, and so we really want to try and minimize the amount of loss in that system. And then there's the crystal itself. So this is an SEM of the photonic crystal waveguide. So you can see the modulation here. And we want to put atoms. This is where we want to put the atoms in this vacuum gap here. And we generate, often roughly kind of 150 unit cells. That changes from run to run depending on what we've put into the to the E-beam machine. So we then take these structures, or these structures are actually suspended across this across a large window. So this is a 2 millimeter by 5 millimeter window. This allows us to gain optical access, so bringing the atoms into and out of the system. And then we suspend kind of 16 devices across here, couple up between 4 and 8 of them for use in the atomic physics experiments. So it's then fixed onto this chip holder here, and then this chip holder then gets fixed onto this big arm, which is on a flange that's going to go into our cold atom experiment. You can see 8 fibers on each end kind of coming out. We're really investigating trying to do free space coupling into these devices, trying to deal with 8 fibers going through feed-throughs and then 8 fibers going through another set of feed-throughs is really quite challenging. So we've made a lot of progress in trying to do free space coupling, which allows us to use really all the structures and not just pick and choose which ones we're going to couple up. So this picture is not necessarily great, but the arm here is that arm I showed in the last picture. This is the chip structure, and the chip kind of sits in here. You can kind of see the fibers coming out from the top. So the way that we're going to deliver atoms to the structure is not the same way that we had before with this kind of side illumination beam, but it's really, we want to deliver kind of a high density of atoms to the sample. And the way that we do that is by creating a magneto-optical trap of cold atoms in the center of this chamber, and then we shine in a dipole trap. So this dipole trap works kind of in the same way of this it's red detuned from the cesium transition, so the atoms are going to be attracted to the regions of high intensity. It's a counter-propagating dipole trap, so it actually forms a one-dimensional lattice, and the atoms are trapped in these what we call pancakes. So trapped in these pancakes, and this is just a picture of the dipole trap itself. So the way that we're going to deliver this system of cold atoms to the structure is, since I mentioned it's trapped in this 1D lattice, if we chirp the frequency of one of the beams, so these beams are passing through acousto-optic modulators, so they pick up some amount of they pick up some frequency from the modulators, and if you put a little bit of a beat note on one of these modulators and maybe ramp it up to some detuning, you can get that the atoms kind of act in a conveyor belt and get shot to the structure. And so we're just going to move them, and then the atoms will arrive at the chip at some time later after they've been accelerated up and then sent into the structure. And so this is an example of some of the spectra that we're able to take in the lab. This is a probe transmission spectrum. where we tune the detuning of this probe to be on or off resonance with the atoms, and then we start the atoms accelerating towards the structure at time 0, and they arrive kind of 20 milliseconds later to the actual structure. And so we're really measuring with this guided mode the absorption of the probe due to the transit of the atoms. So we're kind of sensitive to all of the atoms at all different couplings to this structure in this large scale here. And we can take a cut at kind of 20 milliseconds and extract maybe some spectroscopy information about the atomics, the atoms in the system. So one thing that was kind of challenging is, how are we actually delivering these atoms to the structure? I mean, the structure is small, but it's going to have a kind of complicated diffraction pattern from these really strong dipole beams. So how are the atoms actually traversing this complicated structure of diffraction? And so we went in and calculated the diffraction pattern using COMSOL, and then actually populated this volume with atoms to then try and simulate them transiting towards the structure itself. And so here are the two beams of the waveguide kind of coming out of the page at you. And so this is kind of a zoom in here. This is a simulation of as these atoms go and interact with this system. Oh, okay. So you maybe can make out these are the two beams here and here. They're kind of coming out of the page, and this is an example of each of these dots is an atomic trajectory that's independently calculated and then sent through this structure. So here's an example. So these atoms fly in. A lot of them interact with the top of the waveguide. But there are some that do get into the center of the waveguide. So one of the concerns was that, is this diffraction pattern that's formed by this lattice so strong that it really prevents atoms from going into the center of the waveguide? Another thing that you can see from the simulation is that the atoms should arrive kind of in waves. So they should arrive, depending on the speed of the lattice that you send through the structure, they should arrive kind of in a sort of a phase-sensitive sort of way. So in a more cartoony kind of way of looking at it, this is the this is the lattice. The atoms are trapped in these potentials within the lattice, and then we send the lattice through this structure, and then this probe beam interacts. When the atoms are strongly coupled, you get that the probe is attenuated because it's on resonance with the atoms. What also turns out to happen in this case, which we thought was a problem, but it turns out was actually very helpful, is that as the lattice passes through the structure, it scatters into the guided mode of the structure. And so we can pick that out and use that as kind of a clock as to when the atoms should be arriving. And so you can fold this, you can write down kind of all of this information, fold it back, and get a histogram of the time, the temporal distribution of when the atoms arrive in the structure. And so this is an example of the data that we've taken out from this. You can see this probe is highly attenuated when the atoms kind of arrive at the center here, and not as much out at the ends. So this is kind of this phase-sensitive spectrum is something that, I mean, maybe it seems kind of obvious that it should have worked, but it turned out that it was not obvious at all, and took kind of a long time to get this system to exhibit this type of behavior. So that was kind of a bit painful. So for me, looking at this is very, very exciting. But so that was just that one specific detuning for the probe. You can look at different detunings for the probe, and then you get this kind of two-dimensional plot where where you maybe can't necessarily see right now, but at different times and at different detunings, it looks like they're kind of the system looks, or the spectrum looks a little bit different at different times. And so we'll try to utilize that to determine maybe when are the atoms actually passing through the center. So as I showed in that movie, the atoms are really going to crash on the top, and those are going to interact with the probe that's guided in the structure. And we don't really want those atoms, or at least we don't really care about those atoms, because they're not atoms that could be in principle trapped in the center. And so trying to understand temporally when those atoms occur is really important to trapping schemes. So the way that we tried to parse out those different classes of atoms was by putting kind of a TM mode that would sort of change the landscape around the structure, so that atoms coming in here will see a very different optical field, the different strength of this TM field than atoms that are passing through the sides or passing through the middle. And so what we did was actually take this TM mode and so remember, it's just a waveguide. So essentially, it's just kind of a big lobe that's sticking out on top of the structure. And we detune it blue of the transition. So that means that atoms are going to be pushed away from it and experience an AC Stark shift when they're in that field. And then also, we can also use this mode to actually send in a different laser that's also a TM mode that'll probe the atoms that are kind of arriving in this region. And so I have another movie that's maybe much more interesting. So the atoms fly in, and this TM mode is on, and so they're going to kind of ride up, but at some point they don't have enough kinetic energy to overcome the dipole force that's going to push them away. And so, some of the atoms will make it through the center, but the atoms that do make it through the center are going to traverse this field of kind of high intensity, or at least reasonably high intensity for this structure, or for these modes that are protruding out. So what we wanted to do was utilize this to see if we could, not only in the simulation but also in the data, to see if we could separate atoms out. So here's an example so up here you have no guided mode, no TM mode at all. There's nothing going on. It's kind of what I showed you before. And this is the simulation, and it calculates using kind of a transfer matrix model, which is a little bit maybe kind of getting in the weeds, but calculates what the transmission spectrum should look like for atoms passing through the structure. And as you increase the power on this TM mode, you can see that different parts of the spectrum start to separate and move around. And by going into the simulation, we can see that we're really seeing the same thing in the simulation that we're seeing in the data. And so this tells us that the simulation is really good at reproducing the kinds of things that we can get in the lab. And so, I'll kind of remind you that this was really just to check that the simulation can reproduce what we have in the lab. And so this probe is actually just probing the stuff that hits the top of the structure. And so now what we want to do, now that we've kind of verified this, is take a look at what's going on for the when we probe in the center. So here's a spectrum where we still have this kind of TM mode that's separating out these classes of atoms, and we're probing now the center of the structure. And so what you could imagine probably is going to happen, or is that the atoms that pass through the center are going to have to pass through this region of high intensity for this TM, Stark shifting beam, essentially. And so those atomic transition frequencies are going to be at different frequencies than, for example, the atoms that are passing through the side, because they're not living in this Stark shifting field. And so what you should maybe think about expecting is you would get 2 bands, and look at that. I mean, we end up getting kind of 2 different bands. It's not as obvious as you know we would like, but so we believe that this kind of represents the atoms that are passing through the side, and then right here represents the atoms that are passing through the center. And what we'd really like to do is turn off the probe in some of these different directions, but of course, in the structure we can't actually do that, but in the simulation we can. So in the simulation we can go in and say, okay, well, I really only care about the atoms that are passing through the center, so show me the atoms, all the atoms, which is here, which is kind of what the spectrum should look like, and then tell me where the center atoms are and at what detuning they should essentially live. And you can go into the data and say, well, here's where they should be in the simulation. Do we have considerable optical depth in that part of the spectrum? So in here we do have a reasonable amount of optical depth. So we believe that these really are the atoms that are passing through the center. And the timing really matters. And the reason why the timing matters is because we want to try and trap these atoms. And so one of the trapping schemes that we could employ in this system is to transfer the atoms from kind of one trap to another. So this is a dipole force trap, so it's basically completely conservative. So if the atoms roll into this trap, it should be just like rolling into a trap and rolling out. So there should be really not much friction or dissipation of the atoms. And of course, the time scales are actually really quite fast, so there's not enough time to enact any kind of Doppler cooling scheme or any kind of really like polarization gradient cooling schemes to cool them down while they're rolling in this trap. So kind of, for maybe more, expert in the audience, what you would do is send this lattice in, and the atoms would be in one of their ground state manifolds. You create a trap that has 2 different trap potentials for one ground state manifold, or one ground state as opposed to the other ground state. So as the atoms roll in on, for example, this is cesium, so we're using F equals 3, you transfer the atoms from one ground state to the other. And now they're living on a different surface where the trap is actually very, very deep for this ground state, but now they have time. They're kind of rolling in. There's actually no cooling here, so this is sometimes called single photon cooling. It's not really. You're just transferring it to a different surface where the kinetic energy is the same, but the potential energy of that surface is very different. And so the kind of trapping numbers that we have, we estimate about 2 atoms per pancake, and then every within this dipole bullet, there's about 2,000 pancakes. And so, even with pretty crappy efficiency, you can start to load this structure up. And so we're in the process of implementing this kind of switching from one trap to another currently right now. So just kind of to go over this towards this atom trapping. So we've seen this kind of clock delivery of atoms to the structure, which is something that we had been working on for quite a long time. That clock delivery tells you kind of the timing of the atoms so that you can trigger trapping schemes that will trap the atoms in these structures. And then that will allow us to potentially continuously load this photonic crystal structure with atoms. And this is how we hope to achieve this high fractional filling, which will allow us to really start to investigate these new kind of atom-light interactions in this structure. So in the kind of remaining, I guess, few minutes or so, I want to talk about something that I'm particularly interested in going forward for my own lab, and that's to utilize optical tweezers instead of this kind of conveyor belt sort of implementation. And so I want to take these optical tweezers, and what I'd like to do is, so I talked about this subradiant effect, and I think that this is a really interesting effect, not just for studying quantum memories, but I think it hasn't been experimentally verified yet, so it would be really interesting to try and look at that in a lab. We could try to utilize optical tweezers to see something, some effects like this. This is an example of a finite chain. This is a calculation of a finite chain of atoms that are in a subradiant state, and the only kind of modes, since this is a finite chain, the only radiant modes are actually modes that shoot out the sides, and it really shows you that this is kind of a guided mode of this 1D array. Being able to kind of probe this for uses in quantum memories would be pretty interesting, I think, for the community. Another thing, you can utilize this subradiant effect by looking at 2D arrays, and it's actually a much less stringent requirement on the spacing between the atoms. It's not this lambda by 2 that I talked about. It's roughly lambda, and so if the atoms are spaced by roughly lambda, then in a 2D array, if you send in light that's kind of on resonant with the atoms, all of the other diffracted orders turn out to be suppressed in the same way that this free space emission is suppressed in 1D arrays. And then this atom array actually becomes kind of a perfect mirror at normal incidence. And so that's interesting, just doing nonlinear optics with atoms. But also, I mean, this becomes perfectly reflecting for example, single photon states. And now you can start thinking about entangling single photons with the mirror state of this atomic array. And by utilizing this, it also leads to more scalable infidelities for quantum memories. It's not as drastic as this exponential increase that I talked about at the beginning, but it is, it does improve the scaling for these kinds of systems. So finally, one of the things that I think would be very interesting is to take not photonic crystal waveguides, but take photonic crystal cavities. So you put a photonic crystal here and over here, and they actually form a cavity. So this is kind of your mirror 1 and mirror 2. And you can trap atoms using these tweezers, bring atoms and couple them strongly to these cavities. And in that way, we can try to investigate kind of cavity QED systems, but now in nanostructures. So previously, much of cavity QED had been done in these big, big compared to this, Fabry-Perot cavities. And so trying to do this with lithographically defined structures can lead to kind of on-chip sort of quantum memories. And so these cavities have actually already been fabricated in the past, so they're not a terribly challenging thing to look at. So this is an SEM of one of these cavities here. We can get Qs that are kind of roughly 10 to the 6, so you can start to really look at interesting dynamics, interesting strong coupling regimes between one atom or multiple atoms coupled to these cavities. And then since it's nanophotonics, you can put a whole bunch of these together and put atoms in between, strongly coupled to each one of these different cavities. And so now you're getting interactions between. You can generate interactions between atoms that are in separate cavities, but on the same chip. So not an atom in a vacuum chamber in a cavity over here, and an atom in a vacuum chamber in a cavity over here. But now it's kind of all being integrated onto one chip and one sort of system, and that really starts to look like this. It looks a lot like this, but in a much more scalable way, right? So it's not this this kind of bulky cavity QED that we're used to. It's becoming much more clean and much more integrable into smaller systems. So just to conclude, these atoms coupled to nanophotonics, I think, provide a new playground for studying atom-light interactions. These experiments, I think, are very interesting because they draw on a lot of the advances both in nanophotonics and in cold atom physics. These, I hope I've convinced you, can provide a decent platform for studying not only the collective effects of atoms, which is kind of a new thing that people are talking about now, but also looking at quantum simulation by utilizing this photonic band gap, and then also looking at trying to create quantum memories. And so this is an exciting new field. I think it has a lot of new directions and possibilities, and I think that's largely evident by the slew of theory papers that have come out, and this is just a handful of them, that are really looking at how you could utilize these systems to do interesting types of physics and interesting types of quantum information studies. So just to finish, I want to thank my advisor, Jeff Kimball. Anna Senho she's the theorist behind this subradiant stuff, so I encourage everyone to go and check out her papers on that. Lucas Peng is a graduate student who really worked on did almost all of the work on the simulations, and so thank him for a lot of the work there. These funding agencies for providing the money and the resources for us to do this kind of research. And thank you for your attention.